Hello everyone, welcome to the Exploring Machine Intelligence class, where we study deep learning for artists, and today's topic will be the convolutional neural networks. So the motivation for today is are the convolutional operations. So you might already know something like this. It's a operation which can be used with relatively small amount of numbers, which are block by block applied over the image, and then they have various effects. So maybe the most useful one will be this edge detector, which one sort of processes the image into a representation which highlights the edges of the image. So we can see the interactive visualization of this of the convolutional operation. So here we see an image represented as numbers, and we will apply sort of a 3x3 sharpen effect to this image. And so here is a visualization of how that works. It's applying for some area of 3x3 this kernel of weights, which we saw here, and then the effect that this has on the image is as follows. So there are different types of effects, and there are different types of images. So instead of sharpen, we can have a blurring effect. We can have some sort of custom weights, so change this as we want, or some sort of embossing effect, or the one we also showed before, the outline effect. And so what this is that it allows us to have quite very effective editation of the image or processing step of the image, and we can quite easily see how this would be really useful to have in our network. So we will go into more details about that today. Okay, so the overall distribution of topics today will be talking first about how to split data and how to prevent overfitting of our models, which is something we started with last class in the practical session and left it as an open question, so I wanted to return to it. And then we will fully go into the convolutional neural networks and the operations that are in there, and then introduce some of the real-world architectures, namely the AlexNet. And finally, we will kind of explore how can we use these convolutional neural networks outside of their original area of task, so outside of the classification task. Okay, and so this is a illustration or an explanation on overfitting and on the reason why we should split our data. So let's imagine we have a data set of two classes. One of the classes is dogs and one of the classes is cats, and we have just a bunch of these points. So let's imagine that somehow we compressed the cats and dogs into 2D, and we can therefore plot them in this graph, and so each point is just sort of a representant for the cat or the dog. And what we want is to somehow separate these two classes, and we can see that there are some problems going to happen, right? Some cats which look like dogs and some dogs which look like cats, probably. But we still somehow want to separate this. Okay, and so we can sort of split the data. This would be more or less the ideal, because we can see that there are good enough amounts of samples on each of these sides of the boundaries, and that these samples, which are somewhat strange, are on the wrong side of the boundary, but they don't change the boundary too much. And there are this separation line, this boundary that we are creating, can be either sensible or overly complicated. And so in this visualization, we would sort of consider this one to be more or less sensible. This one to be underfitted, so that's the term that we use when the model is not trained yet, basically. The good fit would describe some hypothesis which is splitting the data in a not too complicated way, and then we would call something like overfitted this line, which, if you notice, it maps the data perfectly, so it splits the two categories completely perfectly. However, we can see that this boundary is just crazy. So if you imagine this case where basically this is the problem of having too complex boundary, is that we have been able to fit all the data perfectly from the training set. But then if some new samples come, so let's say these are some new types of cats and dogs that we see with our model, and their, let's say, representation will fall into these places, right? And so some of them will be classified correctly because they are here, but some are sort of sketchy, tricky, because maybe they are somewhere in quite close proximity to the boundary. And so some images here, or some cat samples here, we would basically imagine that these are very similar to something like this. So we would like to still classify them as cats, probably. Whereas something like this probably is the closest to more samples of dogs. So these should be probably classified as dogs. However, because we created a too complicated boundary here, therefore these samples will actually be misclassified. So this one is already going to be classified as as this class, while these will probably fall here. Even though in the previous plot, so if we used this as a boundary split, they would probably be classified correctly. And so there is a metaphor to be kind of said, or a relation to be said with the Occam's razor. So if we have a hypothesis which is valid for most of the data and is relatively simple, that one will be the one that probably works. But if we have too overly complicated hypothesis, or a boundary which is splitting the data somehow, then it will work for that, but it will be very fragile for any sort of deviation. So if our, let's say, training data had any errors in it or something, or some strange samples, then our model would be too complex, and so it would overfit on the data that we showed it and not be really flexible to generalize over other data that we would show it. Okay, well, so we can see that this is a problem. There are two questions that come into mind, and one of them is if we can actually detect it somehow, because well, how do we see that our model is overfitting? Well, so we can actually see that by splitting the data into training set and into a testing set. And so the testing set is something usually smaller, set aside maybe 10% of the original data, whereas the training set would be maybe the 90% of the original data. And then we would train the model on just the training data, and obviously see the errors going down there, but also at the same time we would test on the kind of left out data, which was the testing set. And we would see that if at some moment the error there is getting much higher, we can guess that what's happening is that the model is overfitting. So in these boundaries that the model is creating are becoming too complex. So something like this doesn't generalize to the general data at all. It is sort of overfitted just on the training set. And so we can detect that by looking at training and testing splits. So that's a good message. We would like to further know how to prevent this situation from happening. So sort of how to postpone this moment where we have to say, oh yeah, now what now, right? Like we still want to somehow get the model better, but not. Yeah. So one of the approaches is to actually stop. So somewhere here on the 20th epoch, we would just have an early stop, and that's one solution. There are different approaches using less complex models, because the ones which are deeper with more parameters tend to overfit more, while having a simpler model sometimes helps. And there are also a lot of tricks which kind of approach this and try to minimize the overfitting. We will actually talk about one of them today, later. Okay. So that was everything about overfitting until now, and I would like to go into the main topic of today's class, and that is the convolutional neural networks. So to motivate us for this is the task to build a better machine, basically. Well, so we worked with images before. We were able to learn a model or teach a model on a dataset of handwritten digits that worked reasonably well, 97% or something. However, we have to say that these images from the MNIST dataset were relatively simple to process. The resolution there was quite small. They were not RGB, they were just grayscale values, and we just had 10 classes. So, and plenty of samples in each one of them. So the task there is basically quite simple, and so that is also the reason why we start with that task. And so we will need to be better at this task if we want to handle larger datasets. And so this is kind of coming from the year of 98 into the year of 2012. Okay, so the one simplification step that we made last class was that we took an image and basically flattened it into a vector. So if this is 8 by 8, we just scan it line by line and flatten it into a vector. Well, what this does to the image is that we can then plug it into our model, which is great, but we have sort of lost the locality of it. So this image, this pixel falls in here, while this pixel falls somewhere in here, and we have no sort of relation maintained in this vector. There is no locality there. So to illustrate it a little bit, this could be any image. So I just chose this one. So consider all of this as just a bunch of pixels. If we look at two neighboring pixels, so maybe something very close to each other, these two pixels, or there's a bunch of pixels there, right? But like, let's say that I selected one here and one here. Then these two pixels, which are relatively nearby to each other in the original input space, will actually probably have something relevant to say to us. So either they will be the same object in the image, or they will be two types of objects, but it's still kind of relevant to us because if it's two types of objects, we sort of know that somewhere in between them there is a boundary that separates these two objects. So the locality there is quite important for us. While if you look at two pixels which are far away from each other, so let's say the one on the cat and then one here, well, they don't have that much in common and they don't really tell us much. So the previous approach, where we just took all the pixels and flattened them into a vector and then basically without any correlation worked with every one of those data values, is not the best. Okay, so this all sort of feeds into some studies made in biological sciences, where in 1962 there was a study on the human visual system and or animal visual system, and they discovered two types of cells. So one type was a sort of localized cells, which were firing when some sort of detail was present in the image, so they were processing details. And then some complex cells, which are somehow covering larger areas, so they are processing information from much larger area than from just a single unit. And how this happens inside human visual cortex is probably quite complicated, so we don't have to go into that. But this concept of having two types of cells is something that has been used later as an inspiration for the networks that we will use, or we will talk about today. So the first one is kind of the really first work which worked with this concept was a paper from 1982, which introduced a model called neocognitron, and you can see that this is actually before the papers that we discussed last class. So this was sort of a experimental stuff, and then this worked as a predecessor to convolutional neural networks. And so similarly, like the study of biological visual systems, they attempted to create an artificial visual system which would also have two types of cells. So sort of focusing on a single image feature cell, and then one which would be combining information from an area. And how to imagine that is basically some illustration like this, where we look at a larger image or like a larger area, and then sort of just reproduce that bit, and then just reproduce that bit, and then just reproduce that bit. So what this means actually, and how it's processed in convolutional neural networks, we will sort of look into that later in the additional slides. But let's just see the video which was attached to this work and about neocognitron.
Now let's see the ability of the neocognitron. Using the principle of the neocognitron, we have designed a system which can recognize handwritten numerals. This system is operating on a mini-computer, and it can even operate on a microcomputer. Let's draw a numeral 2 on the tablet.
From the analysis of the stimulus features, the input pattern is recognized as 2.
So while this is quite funny, because the whole style of this is just strange, and the way how they are reading it out as well is quite funny, we can sort of see the same dataset that we worked with before, the MNIST, and then these strange blocks which are somehow processing the information well, while looking at the locality of the images, right? So they are somehow better than what we were showing before. And I think I will just jump into this inspirational message. Oh, at the end.
Not have yet, which modern computers and pattern recognizers do not have yet. We are continuing our research, and we hope to develop an artificial brain closer to the human brain.
Okay, let's develop an artificial brain then. Well, so this is just a sort of illustration, sort of almost like history of the research, and yeah, let's actually talk about what's happening. So, an operation of convolution is something which works with the original image, which is this thing, the input, and then usually the convolution is defined as some number by some number sized kernel. So this is 3 by 3 block which is jumping over the data. And so what this means is that we will look at the same amount of pixels from the original image, 3 by 3 block, and then look at the kernel. So this is bunch of weights, which is again 3 by 3, and then we multiply these two together. And so how this happens is it's an element-wise multiplication. So it's not matrix multiply in this case, but it's looking at values from here. So this would be the input block from x1 to well, this is x9 in this case, and then this is multiplying with these weights w1 all the way to w9, and then sort of like in every block we just multiply these two values. So we would have x1 by w1, x2 by w2, etc., all the way to x9 to w9. And so then what happens is that we want to somehow compress this into just one output. And so what we do is that we sum sort of these numbers over this area. And so if you would like to write this as a formula, you could say that you sum it, and then you sum it into this this formula. And I will just vaguely say that if you remember, this is something that we have seen in last class as well, when weighing in a input of a dense or fully connected neuron layer, or just a single neuron unit actually, you would have the same operation there. So it somehow, in the end, will neatly all fit together into a usage of the same operations. Okay, and so this is a way how to kind of calculate from 3 by 3 region, convolve this kernel, these weights over it, and then have some sort of output. And so what happens next is that we taking this one single pixel as an output, this is 1 by 1 from 3 by 3 area, we will then jump and sort of jump one pixel to the right in the input space, and then this also means that we will jump in the output space by 1. Well, what is important to kind of say, and you will see this later as well, is that these 9 weights that are here, we have just reused them. So we are sort of using the same operation, kind of using the same processing filter, and just applying it for the kind of consequential frames in the original image. Okay, so we kind of continue this way all the way till we basically scan the whole image. So if you look at it, these weights are basically reused for everything. They are always the same weights for one convolution. And if you look at the original image, we have kind of processed this block to create this pixel, then this block 3 by 3 to create this pixel, this block to process this pixel, and this sort of applies everywhere, right? So every one of these output pixels would correspond to a block of 3 by 3 pixels there. And just to kind of bring this into the context of what we are talking about before, this is actually somehow measuring the locality of the image. So this is somehow combining the information present in all of these 3 by 3 pixels into this one pixel. And so the choice of 3 by 3 is arbitrary. You could have said that I want to look at 5 by 5 area, and then you would be looking at 5 by 5, multiplying it with 5 by 5 amount of weights, and then getting 1 pixel as well. Okay, and so there is some sort of terminology here. We talk about these as weights, and then this operation as a sort of filter, which is happening and kind of influencing the data somehow. And because it's jumping over the image, it is being applied everywhere, it will produce another sort of image here as well. And so, yeah, one thing to note is that convolutions were used even before neural networks, and they were sort of the sort of processing function, a filter that you could apply to an image. Okay, and so there are 2 details here, kind of. Maybe let's talk about this one. You sort of already can probably notice that this pixel doesn't really have the corresponding input pixel here because it's stepping outside of the boundary. And so in that case, you could either say that, hey, let's ignore him and we will not have this pixel, but we would produce just a smaller image at the output. And because people do kind of want to keep this resolution the same, because then the math becomes easier, and also it sort of handles the resolution the same way, when it's propagated through the network, then we can sort of trick it in a way that when we are asking to create this pixel, we consider all of the non-existing pixel in the input as zeros. And so this is called zero padding. In a case where this is 3 by 3, we have just 1 pixel sort of boundary around the whole image. We could have more if this block was larger. And the second detail is that we talked about weights here, and that is sort of neural network machine learning terminology. But when we because convolutions is something that existed before, we use the word kernel to refer to this block. So we could say that this is a filter that we apply over the image, or and that it contains weights, which are these numbers, or that it's a kernel and it has some numbers in it as well. So these are sort of the same. These mean the same thing, but they are different terms for it. Okay, and so this was still relatively theoretical. Let's illustrate it on these images. So if we have this input image and we apply this 3 by 3 filter on it, we are stepping 3 by 3 here, and you can imagine that every pixel here corresponds to a whole area here. Then these values are sort of weighing in values from the neighboring pixels. It doesn't really matter what these values are, but they are 1/16, 1/8, 1/4, and then sort of the effect that this has is to blur out the information. So you will see that this is a kind of blurring effect. Another type of effect would be sort of embossing, which is something like this. I guess you might know these filters or these effects from some image editing software. And what they are using is some sort of convolution, probably. And so this is some effect which will somehow highlight the the 3D information, so the edges, and even better would be the outline, which is even more kind of highlighting the sort of difference between frames, I guess. And it's doing it by doing this convolution. Well, to look into the details of this, again, I will open this website and probably, yeah, here we can see it quite nicely. So on the left image, we can see that there is a 3x3 sort of input area, and there we can see this 3x3 kernel, which is the sharpened kernel, which means that these weights are used, kind of have been found manually to figure out that, hey, this actually, if you apply this over the image, it will sharpen it, right? And so if I'm moving my cursor on the left image, I will be getting also a visualization on the right side, which sort of tells us which image or which output pixel this kind of changes. And if I see the border, I can sort of almost get out of the image, and then you would know that I'm getting zeros in this formula, right? This is empty pixels which don't exist. So this is the zero padding I was talking about. Yeah. Okay, and there are different. Let's just see maybe the outline one. Okay, so it's sort of getting the difference between this pixel and everything around it, which is sort of the edge detector. Okay, well, so we can see that these are quite like powerful edit operations. These three especially, and you can imagine that there are more like this, right? And some specialized just for one type of edge, for example. And so this is quite cool, and this is something which has been done really simply because we just have 9 numbers which will do this really complex operation to the image. Well, somehow we would like to include this magic into our neural networks. Okay, well, so the question is, can we do this somehow automatically? Because similarly, like in previous cases, where in your homework you had to sort of manually find the weight values for the inputs and sort of really like sit down at it and sort of compute, do the math, and calculate what it would, which effect, which weights would sort of separate the data that's coming into the classes that you want. Well, you could do something similar here, where you manually find these values, and people have done this. So these are sort of ones which have been found manually or theoretically, and then you could apply these already, pre-process your image. However, the question here really is if you can somehow get these automatically. So, well, I will say, I will reveal to you that yes, these weights of the kernels are something that is changeable during the training of the model, the same way as the weights that we had in the fully connected neurons were also changeable. And so, how to connect these convolutions with our neural networks? Well, so in addition to the fully connected layers, so you can imagine that there is a lot of neurons, not just 2, but let's say many, and that this would be one fully connected layer, or a dense layer, as we also refer to it in code. We had some parameters for each one of these connections, and there are many connections here. You can imagine that instead of having this as one of the layers, you could also have a convolutional layer. And that layer is taking in an image and then processing it into another image. And so we could repeat this process layer by layer again and again and have a bunch of operations of convolutions, and then eventually at the end sort of say, okay, that's enough, and then connect in these fully connected layers, and then sort of scan the image same way as we did before, flatten it into a vector, and then plug it in here. And so that almost separates the model into 2 parts, which we will talk about later, and then call them names and stuff, define them a little bit as well. But this is just an illustration that we can sort of plug both of these things inside our neural network architectures. Okay. Right. Well, there are a lot of differences there. One is in how it processes the images. So if you look at the fully connected layer, if you imagine that there was an image at the start, and then we plugged in a neuron here, we were calculating x, y, w, y, which is nice, and then doing this with all the inputs for this one particular neuron, and with this is just 5 by 5, so this would be 25 corrections. But you can imagine that with larger resolution images, and we sort of wanted we want to process larger images. In the intro we were saying that 32 by 32, no, 28 by 28, which is the MNIST, is not enough for us. So we somehow want to include much larger images here, and this would basically skyrocket and explode because there would be too many connections here. And the problem here is that every one of these connections is a weight, is a parameter that we have to set up, and that becomes much harder to figure out on one hand, and also the complexity of the model is kind of skyrocketing. So if you remember from the start something about the overfitting, if we did this, we probably would have problems with overfitting. Because the model would be sort of remembering the data rather than being able to generalize well. So, to bring this message to the end, well, the number of weights in this case is a lot. And if we look at the other type of layers, which is the convolutional layer, well, we have a image at the input, then we have the convolutional kernel, or the weights here, and then we are taking this as one pixel output. Well, and the important thing to note between these two is that here we also have an output as an image, sort of. So as an image, whereas here we would be getting a vector. So this is almost like a matrix, where this is a vector. Maybe what is relevant now is that the number of weights here, it's depending on the size of the kernel that we chose. So if we choose to look at 3 by 3 area, we need to figure out these 3 by 3 numbers, which is 9. However, we are applying the same 3 by 3 numbers for this square, then this square, then this square, and basically for all the image, over all the image. So regardless of the image size, the number of weights and the size of the kernel is the same for any image size. And then the number of weights depends on the size of the kernel. So it's again the same. It is fixed for any input size. So this is maybe one of the largest important differences, is that the number of weights that we have when using convolutional layers is much lower. One additional kind of cool thing here is that here we are sort of maintaining the locality of the image, right? And so here we flattened it, basically. We didn't consider the proximity to have any relevance there. The way how this one is added to this formula and this pixel is added to the formula is the same, even though the pixels are really far away from each other. While this pixel here would be processed into one output here, and this pixel would be processed into another, somewhere completely different. And the locality is maintained in convolutional layers. So this would be the differences, sort of. Okay. So there is infinity of details I can sort of give you, and all of them are sort of increasing the capabilities of the models and everything. But I will kind of stick with the ones which are important. And one which is quite important as well is the pooling operation. So we talked about convolution. So let's imagine here is an image which is being transferred into another image by this convolutional operation. And so this is one pixel which is derived from, let's say, 3 by 3 area. There is another type of operation which is called pooling. What it does is that it just simply scales the image down. So if we had large image here, what happens after the pooling operation is that we just scale it into the half size of this. So we call these in different names. We can call them pooling layers, we can call them downsampling layers, and what happens is basically just scale it down. You halve the image height and width, basically. If I were to relate it to some sort of like operation that you would do in Photoshop. we would just scale it into half. Okay. Well, so why in the earth would we want to do this? Well, one of the effects is this one. Well, we would actually be getting much less information. So if you imagine that this was, I don't know, 1000 by 1000, and if I were to connect a pixel like a neuron here, I would be connecting with all the pixels. And so if you downscale it, you are connecting it to half on both dimensions, and so 1000 by 1000 versus 500 by 500, and well, 500 is still quite a lot, but you can see how this would scale down quite drastically. So we are reducing the amount of information, and so this means also less connections for the later fully connected layers. So this is just one of the effects. Let's say that we didn't want to connect a fully connected layer yet. Let's say that we want to connect another convolution here. Well, so if this was 3 by 3 area into 1 by 1 pixel, and then again here 3 by 3 area into again 1 pixel, and we pooled the image or downsampled it by half here, what happens is that the later convolution, this one, so the operation which happens here, is looking at this area, which no longer corresponds to just 3 by 3 pixels in the original image, because this pixel here, like the left, the first pixel that we have here would relate to this whole area actually, and the last pixel here would relate to this whole area here. So this is no longer just 3 by 3, but in the original image dimensions, basically this would relate to much larger area. And so what this actually allows us is that these later convolutions can specialize on looking at larger parts of the image, whereas these earlier convolutions can specialize on working with sort of smaller areas of the image. Well, to put it differently, or to say differently, is that every one of these convolutions can specialize on processing different scales of the image. So while this is sort of focused on 3 by 3 regions, which is maybe this one is focused on details, these later ones, and this can mean one operation later, or this can mean many convolution and poolings later. This convolution here can sort of focus on larger areas. So sort of focus on concepts rather than details, such as, for example, you would have some edge detectors here maybe, and here you could have some much larger concept detectors. And I will not lie, this is huge. This is probably the most important thing that's happening in the convolution and pooling operation. This effect that it can separate these the task that these processing units have. Okay, what this means visually, well, we will see it now, or later actually. Yeah, we will see it after the pause. Because I wanted to add one more detail, and then we can have like a short rest, and then return to the slides and to actually visually seeing what the separation of detail and concepts, what it does. So I wanted to say that sometimes reading these sort of diagrams of having an image and then converting it with a convolution into another image, this can be quite complicated to read when it becomes larger and the model is larger. We have just a bunch of these operations, and in the publication somewhere they don't explain every step. They will sort of compress the information quite a lot. So this is a sort of guide how to read these. Well, so in a single convolution that we have here, we are converting from 2 to 4 image into another 2 to 4 image. And this one operation is a single convolution which will have 3 by 3 weights. So this could be sharpened, for example, but it's also can be anything that that we just automatically found. So it's a data-driven convolution, data-driven weights. Okay, so this is a single one. If we add another convolution to this, so we want to somehow process the same image, and if the first one was maybe sharpened, we sort of want maybe the second one to be, I don't know, maybe blur, or maybe the embossing effect, or something like that, right? Or any other effect that the network on its own sort of figures out. Well, so if we add another convolution, we will have the same output, and we can sort of say that we are adding another, almost like a channel, right? We are adding another sort of width by height matrix, which is the same as the original, and we can collate them, and we can say, hey, we have this output which is the same as here times 2. Okay, well, this scales, and usually actually in the architecture designs you would not see only single convolution or just 2 convolutions. We would see just a whole layer of let's say m convolutions. And so if we have many convolutions here, and many refers to m, we would have m effects. So each one of these sort of matrices inside this box, each one layer in this box is basically one result of one of the convolutions. So we have m convolutions, so we would have m layers, and each one is sort of a different effect. Okay, so this is what happens with the activations, or with the shapes of the outputs, basically. The input shape would be here, and this output shape would be sort of this. And what happens with the weights is that we have 3 by 3 for each one of these convolutions. So if we have m convolutions, we have m times 3 by 3 weights. Okay, and the 3 by 3, by the way, it can be any number different than that as well. I think 7 by 7 are used, 5 by 5 are used, or 3 by 3 as well, and other, of course. Okay, so this was just a small detail to sort of help you out later when reading some more complicated graphs, because yeah, just don't be scared about these boxes, because they just mean that we have processed this with many convolutions. Okay, so right now let's have a pause, and after the pause we will start visually sort of showing what we talked about before. So the concept of details versus some larger concepts inside the image, or inside the network as well. And eventually we will get into how to use these networks. Hello and welcome back after the pause. Let's continue where we ended, and that was kind of conceptually talking about the way how we have convolutions and pooling, and how this affects the convolutions to be specific on for different scales. So we can almost talk about the convolution into pooling repeated as a combo that we can see over and over in various convolutional neural network designs. And this means that this block with convolution, pooling, and then convolution, and then later again pooling, is sort of repeated over and over. And so what this allows the network to sort of learn is that in these 3 by 3 blocks, it will convert the image into just 1 pixel, and then in these further 3 by 3 blocks again into just 1 pixel. And what this actually means that this 1 pixel here is sort of responsible for a whole area in the original image. And this one is basically larger than 3 by 3, or yeah, there is some sort of like this pixel corresponds to this 3 by 3 area, and the pixel which is 3 to the right of it corresponds to the 3 by 3 area here. So there is some sort of chain. We can actually calculate the exact number here, but it doesn't really matter. The concept is about being able to sort of target larger areas. And sort of the deeper we get in this convolution to pooling combo, the larger area this 1 pixel would sort of represent. Okay, and so there are different ways how to visualize this. We can start with this one, and this shows the kernel visualizations, and shows sort of the kernel visualizations for different for different convolutions. This depth dimension sort of shows that these are some of the early convolutional convolution operations, so some kernels from the early stages, whereas these are somewhere in the middle, and these are somewhere from the deeper parts of the network. Well, so this is one sort of visualization. I think there are many other types, and this is a sort of there are many ways of visualizing it, and sometimes they are just proxies to show some sort of concept behind it. So they might not be necessarily the exact values that are, for example, in the kernels. These are some sort of visualizations. However, what we can sort of see from this is that in the early layers, so sort of this ones, for example, we can see only some localized features. So what these layers are firing on, or these convolutions are firing on, are sort of just detectors of types of edges, basically these. So we can see that this detector has learned different types of edge detections for a lot of these, or actually some sort of circular features here, which would maybe correspond to some like full area which is white and full area which is black. We can see also some detectors for different types of small shape primitives, or some colors, or detectors for edges, or detectors for example, higher to lower frequency boundaries, which means that maybe one part is something with a lot of detail and the other one with quite blurry background. So again, that would be a sort of edge detector. So all of these would be somewhere in the earlier layers, whereas in the later layers, we have sort of more higher level general features. So we would have sort of like bigger parts here basically, and all the way to sort of concepts. So this is a detector for faces. So of course that it would sort of have these features of faces saved up. So we can actually see these concepts here as well on this visualization. So if we show this again on some different types of data, this is basically the same type of visualization, but for cars, for elephants, or chairs. We can see more or less the same early level, low level features or visualizations of those features in the first layers, because all of those types of objects would have these edges basically. However, in the mid-level and the high level, we can see that they are sort of specializing for detecting, I don't know, car parts, elephant parts. So a lot of like, okay, this is an elephant behind, I guess, or something like chair parts, and then actually getting some sort of high-level concept in these later stages. So again, this is a sort of just a visualization. There are many types of visualization. There is a novel one from 2020, which is quite cool, but it looks like it has a really high resolution of everything. So it might be quite like, I think their methods of visualizing it are somehow sort of edit. So it's not exactly showing what is in there in the weights, but it's sort of just propagating it back and forth to see what types of images they would fire on and everything. So they are it's interesting read, honestly, but maybe it looks too advanced, sort of when you just look at it, while the operations behind it might still be the same 3x3 convolution or something. Okay, and so we can sort of see this sort of path from going from the input images, exploring the low-level features, extracting sort of higher level features, all the way to sort of almost conceptual features. And when we get these features, we can then classify them sort of like, oh yeah, I mean, I know these elephants because they are the first elephant I was shown, and they are these other elephants, which are the elephants that are shown on the, I don't know, other types. Or you can start recognizing cars if you describe them using these higher level features. Or the same with the faces and for identification. Okay, and so there is a nice visualization for of convolutional network as well. So we know this from our first presentation. This is basically the same thing that we saw before, only for a convolutional neural network. So if we start by drawing like, okay, let's try to have a nice 2 here. All of this lights up, and we can sort of see what happens with these blocks. Each of these blocks are sort of the outputs of the convolutions and other types of operations. So here we have the input, here we have 1, 2, 3, 4, 5, 6 convolutions. So this is the first convolutional layer, which has 6 convolutions, and each one has learned a different sort of detector, let's say. And so if you look at these lines which are connecting the original input image with these sort of processed images, these I think it's 5 by 5. I think these 5 by 5 lines show us sort of the 25 parameters that this particular convolution has learned. So you can see that this one has a especially strong connection with the lower left half. There is one really strong network, whereas this one would have, yeah, this one also similar one. Yeah, this one is firing all over. Maybe all of them are sort of firing, right? So you can see these lines. They show the weights in the kernel or the values inside the kernel. Okay, so yeah, just to bring it basically before, the lines there are basically these values that we have here. Except they are sort of custom made. So if you fill in some numbers here, you can sort of have any sort of effect. You can mess it up with yeah, you can change the operation, have different sort of classifiers here or extractors here, and this is basically what happens with these lines. Okay, so that's one. And the second sort of thing that we can sort of look at is that when we convert this image using this particular kernel, we get this as an output. So these images are visualizations of how it looks when you process the image with this one particular kernel. So we can almost see what they are doing. So this is maybe even the lighter number means higher activation. So this is a sort of I guess a detector or extractor for edges which are on top to down area, because it's firing sort of around here, because it's firing around where the change happened. So this is a detector for changes between boundaries, between top to down. I guess you could say the same here for the left to right changes, because you would be getting a lot of sort of activation here, and actually here as well. So maybe the edges it's detecting are sort of on this line, and here would be again some maybe like this sort of line of detection. Yeah. So to unpick what's actually happening is sometimes quite hard, because you don't know really exactly what will happen with the later layers there, right? How will they sort of plug it in and out? But you can sort of say about these concepts. Okay, so this was the first convolutional layer, this one, and what we can see next is this one is the first downsampling layer. So this image is basically just this image, but made into a half. And so you can see 4 connections, and basically what happens is that they look at these 4 values and get an average, and then just create the 1 pixel from that. Well, that's what would happen in a Photoshop if you said, okay, I want to scale this image into half of its size. It would again sort of like pick where which pixels it's coming from, and use some sort of like averaging between these two. So the exact type of operation you do, if it's average or if it's some other type of operation, is something that you can also set. But that's kind of just too much detail that we don't need to worry about. Okay, so we had input, first convolution, first pooling, and then we have this strangely looking layer, which is the next convolutional layer. And so because here we had just one image of just gray values, we have just basically one channel here. We can consider, whereas here we have 1, 2, 3, 4, 5, 6. We can consider this as 6 channels of the image. Then this next convolution is sort of combining using the same sort of weights for everything. So if you are moving pixels around, you can see that the weights are always the same. It's connecting with some previous channels from the image before. So you can imagine that if here we have RGB, so if this wasn't just 2 with 1 channel, these connections already would be kind of connecting with some pixels here, the same sort of area there, and the same area in the last channel as well. So that's what's happening here. It's picking some channels from the previous layer as well. And so the amount of weights is larger, I think it's 4 times 5 by 5, but it's still less than we would have if we were connecting everything with everything. Okay, well, cool. So this is the other convolutional layer, and here you can see the other downsampling layer. So you, like, while we almost could unpick what this sort of detector does. In here, it's much harder to see. You can see the shape of the two here as well. It's because the location of the image is still kind of being maintained all the way from here to here. Only it's being reduced and reduced in size, so because of the pooling operation. So it's much harder to read, but there is still some locality there. Okay, and so these were all the convolution pooling, and then what happens later is that we will plug in the original fully connected neural network to it, and as we know, that one has to connect all its neurons with all the previous inputs, and so if you look here, this is quite just the madness, because we have every neuron here connecting with every possible input from the previous layer. So there are a lot of connections here. But you can just imagine how many connections there would be if you were connecting with everything here, for example. So that's also why we have these pooling operations, because they are reducing the amount of information we have. Okay, so this one is connected with everything, and then this one is again connected with everything, and then this one is again connected with everything. So these three we sort of know. These are the fully connected layers we were exploring last time, and this sort of setup of having a bunch of convolution to pooling layers followed by some fully connected layers is a design that we will see again and again. Okay, so let's return to the slides. Okay, so this was some sort of intuition that we got for the sort of intuitive understanding that we got for the classification networks. The lower features in the convolutional network will sort of correspond to one thing, and the higher level features will correspond to other things. So let's say that we want to bring some sort of intuition for our generative networks that we will use later in the class. It's not surprising to say that we will see some convolutional layers there as well, because it's simply just the thing that sort of works with images quite well. So we will be using those again and again. And there will be similar sort of process of having convolution pooling, similar sort of setup in a different way, but there are some details that we will have to address later. But we can all again sort of differentiate between some features being high level and then some being low level features. Okay, so let's say we can hack into these, right? We can hack into some of the convolutional layers of the generative model. And what I mean by hacking is that basically we can sort of get the values, the weights from there, and then just sort of start changing them somehow, or maybe reconnect them, or maybe start changing the activations that are feeding through the network. Why would we do this? I guess we are trying to sort of change what the output of the generative model is. There are many ways how to do that, but this sort of hacky way of having a trained architecture and then trying to move with that architecture rather than moving with some inputs is a sort of interesting thing that is I think this is something that is still being sort of explored. However, even in that area, we can sort of get some intuition from the convolutional layers. So something that we just talked about, and that is that if we target some high-level features, so something which is sort of working with the very with the really small representation of the image, when the image is condensed into just few pixels, then the changes there will sort of very drastically change what we are seeing in the results. So we are sort of jumping from you cannot really know what's stored in which convolutions where, but let's say that there are some filters which are sort of responsible for creating forests, and then some which are responsible for creating cities or something. And if you mess with the early resolution versions of it, which are sort of working with high-level features, you are changing the categories completely. So you are sort of changing from a cityscape sort of into a landscape which has a much less city or much more sort of forestry in there. And you are sort of also encountering some glitches, which is also quite interesting. And imagine that this can happen in with any sort of dataset, which is with any sort of generative model. So this doesn't really is not really limited only for this one dataset. Okay. So if we are sort of messing with the higher level features, we are sort of changing the large concepts of the image that we are creating. While if we were to target convolutions which are of the low level features, so something sort of later in the architecture of the generative networks, which is something that we didn't talk about yet, but there are convolutions that we can sort of relate to now already. Then the stuff that will be changed in those images will be the same as what we saw in the classification networks. So some sort of details or textures, only sort of very localized changes. So if we were sort of changing with the same force in this case and in this case, but in the case where we are targeting the low-level features, we are only sort of just changing small details inside the image. But basically, the whole concept of the image, I guess, it being a cityscape, is not really changing. What is changing is some small details in texture or in the actual details present in the image. But this is a sort of intuitive understanding that we can get from understanding what's happening with convolutional layers. So it's actually sometimes useful to know what convolutions will do to be able to understand what changing these convolutions, what effect will it have, and why. Okay, so let's bring this back into a more from the more visual illustrative examples. Let's bring it back into more abstract description of the architectures that we will be seeing. So what we are talking about all the way until now is introducing the convolutional neural network architectures. And most of them will follow this very simple layout. Well, it is actually quite simple. So if we have an image at the input side, we will have some area where we are sort of combining convolutions and then poolings, and then repeating this whole block again and again. So as you could see in the interactive example, we had one convolution, one pooling, and then another convolution and another pooling. So we were repeating this block twice. How many times you repeat this block will depend on your architecture, basically. It also will depend on how large images you want to process, because in each of these pooling operations, we are reducing the dimensionality. So if we were to reduce the dimensionality too much, we would have, I don't know, really small image somewhere here. The loss of detail would be too much, I think. So you have to sort of adjust these architectures into what types of data you have or what types of tasks you want to do as well. However, we sort of can see that in various designs that there is a repetition of this part. And then when all of this is done, the output here would be some sort of block of images again. And at that moment, we sort of flatten everything and then say, okay, you are no longer a block of data that we want to treat with sort of like local information. We want to flatten it and then work with it as with the fully connected layers later. So if we were to translate this image into a sort of formula, which is very arbitrarily written, but like let's say that we have an image which we convert into, which we kind of plug into this pipeline of some repetition of convolutions and poolings, and then later flatten it here, and then plug in some fully connected layers, which are again repeated, maybe there are two, and then eventually we will link it into a label. So all of this is the model, and then these are the inputs and these are the outputs. Okay, so let's say that this is the formula that we will be working with. And this is a general convolutional neural network architecture design that we can see again and again occurring in various networks. So we can see that this part, this image to convolution to pool to convolution to pool to convolution to pool, however many times you want, we can call this part as something as a feature extractor. This part of the network is responsible for extracting relevant information from the image and compressing it eventually into the flattened vector V. So at the end of this repetition, we will flatten the layer and then get some sort of vector which is a representative of that image. And so if we have fed it with an image here, we will repeat some operations that are sort of processing it and pre-processing and post-processing and doing some effects on it. And eventually, we will actually get back into a vector representation. So here we have some matrices and everything happening, but here we actually convert it into a single vector from image into a vector. Okay, and so if this first part is called feature extractor, then this later part is called classification, or is responsible for classification. This part is responsible for classifying this vector that we get here, sort of, and then representing it. This is a representation of that image that has been processed here, and then assigning this representation with a label. Okay? So if we carry on with the terminology, we can call this sort of intermediate step inside the network as a feature vector. So it is a sort of compressed representation of the original data. Why am I saying compressed? Well, imagine that you had a 1000 by 1000 pixels by 3 channels sized image and the input. Well, when the network is done with it, when the feature extractor is done with it, it will flatten it into a vector, and maybe that vector will have maybe 4096 numbers, or some other number, some other amount of numbers in a vector. However, if you were to imagine the 1000 by 1000 by 3 numbers here compared with just 4000 numbers here, then you can see that there occurred a sort of compression because we extracted just some values from here. Okay, and later step will be to come from this representation, this feature vector, and then classify this vector, these 4000 numbers, into a label. And the label can be, I don't know, it can be the numbers 0 to 9, basically, in the demo that we saw before. Okay. Okay, and so as far as our understanding goes, this is the splitting of a general convolutional neural network architecture into 3 blocks, sort of feature extracting part, classification part, and then some sort of intermediate representation that we can see here. And the really neat part of this whole process is that this differentiation of function emerges automatically when we are training the network. So we are not kind of manually forcing it to do this. We are not we didn't have to specify what it means to extract a good feature here, and we didn't have to say what it means to actually classify those features. We are not writing these blocks separately. We are sort of training the whole network end to end, which means getting something at the start and then getting something at the end. And by creating this architecture in the middle, we are forcing it sort of to automatically derive these functionalities. So this part will have to sort of get a decent feature extractor part here, because it somehow has to propagate the information from this side all the way to this side, and it has only 4000 numbers here. So it has to somehow compress it. And this part then somehow still has to go from the vector representation into the label. And so all of this is sort of data-driven approach to feature extraction and to classification. And so I think in previous years, and in previous sort of before machine learning happened really, or before the revolution happened, and actually even still in some research now, what you would see is that some parts of this pipeline, you can say, some parts of this pipeline are done manually. So there are some pre-processing steps that would sort of replace this entirely, and then you are trying to sort of do the classification later automatically. But the magic or something of neural network architectures and this sort of learning is that you are going from a end-to-end point, and you are sort of leaving it at the discretion of the machine to figure out all of this. Well, so there lies its strength, but there lies also its weakness. So if you have rubbish data set, too small, too biased, too with some error labels, basically, all of this will happen, and the machine will learn this, and it will include all of those biases, all of those errors, all of that inside it. And so you are sort of, you cannot really track what is happening at that moment, or people are trying to visualize it, right? That's why we have all of those visualizations of those features, because we sometimes we want to keep some sort of control over what's happening here. But simply put, if you have rubbish data, then this network will learn rubbish features as well, or rubbish feature extractor functions as well. So it all sort of revolves around that. Okay, so let's step from the general description of a neural network architecture, of a convolutional neural network architecture, into one particular example that has been used in the real world on some real world data, and that would be the AlexNet. So, what is this AlexNet architecture and this AlexNet model? Well, so the AlexNet model was something created in 2012 as part of a competition to detect some images, and the architecture of this model is something that we can almost read entirely now. So we have a 224 by 224 image on the input with 3 channels RGB, so we can see that it's actually plugging in some real images now, not only MNIST data. And then these operations follow with convolutions, which we can sort of see with these 5x5 filters, 11x11 filters, 3x3 filters, 3x3, 3x3, etc. We can also see some sort of pooling operations, so reduce kind of downscaling operations. So it's going from basically halving the resolution of the image here and here again, more or less, and then it is following with additional convolutions, and then in the end it's sort of going from the realm of extracting features into a vector representation somewhere here, which is followed by a fully connected layers. First fully connected layer, second fully connected layer, and then some last layer, which is again a dense layer or fully connected, which has 1000 categories. So even just by looking at this sort of architecture design, we can sort of see what's happening. We have an image of 224 by 224 by 3 RGB, and then we are classifying it into 1000 categories all the way here. Okay, and so maybe this image is also why I was sort of trying to explain how to read these strange blocks, because we have some resolution here, and then the amount of channels of the convolutions. So in this case, we had 11 by 11 convolution in this operation, and we chose to do 96 of them in the first layer. So this represents 96 outputs of the 3-channel input. And this sort of repeats again and again and again. Okay. There is one more detail to sort of explain, and a trick which they used in this paper, and that is called the dropout layers. And yeah, I will go into that. So what dropout is, it is a way how we are connecting between one layer to another layer of neurons. So we can imagine these to be fully connected neurons. Everything is connected with everything. And what dropout simply does, it that during the training, it deletes some of these connections sort of randomly. So we started with a standard neural network here, which had all the connections, everything connected with everything, and then applied dropout, and with some probability somewhere, which we set up in front, some of those connections were dropped, and so basically the amount of connections was reduced. Well, why would we want to do something like this? It's a good question. Well, this sort of prevents the network from creating overly complicated mappings. So in here, if we want to output one sort of particular label for this one image, there are quite a lot of ways how to map this sort of function, right? There are many ways how to represent this data inside this network. And if you remember from the start of the lesson where we talked about overfitting, if we create models which will learn these boundaries, which are really complicated and like kind of too complex in terms of the classification boundary, usually when you let the network to work with all the neurons, it will sort of create a really complicated net of neurons which are depending on each other to somehow map something. So to sort of almost so a network which has all the neurons in it is much more it is much more easier for it to remember all the training data set, all the training data that we showed it. While if we actually cut some of these connections randomly during training, we are almost telling the network while training it, hey, don't depend on too overly complicated connections. Basically, it sort of prevents the network to rely on too many neurons at the same moment. It sort of it changes these values over time, right? And during the training, it sort of tells the network that if you are able to map something with just few neurons, and the few neurons are something that will more likely stay in the final graph because we are randomly dropping some of them, it will maintain that rather than being sort of like forcing the whole net into remembering something with the usage of all the neurons. So dropout, so this sort of method, is a sort of is a widely used technique which helps with overfitting. Okay, and so if I go back one slide, how you use dropout is that you will sort of add that as an operation inside these in between the other layers. So you would sort of drop some of these connections with some probability, and then drop some of these connections with some probability here. And what it does is that during training, it will sort of force it to create a more, rather than creating too complex explanations, it will sort of keep it simple but working. So sort of like, yeah, the intuition behind it is to rely on simpler explanations. So sort of using the Occam's razor as a hypothesis rather than something which is too interconnected. Okay. Yeah, so the exact functioning of dropout are more or less like a detail that we don't have to care about too much. We care about the functionality of it, which is that it helps with overfitting. Okay, so to explain slightly the context of the AlexNet network and how it was created and what it was used for, we will introduce the ImageNet competition. So the ImageNet is a dataset of 1.2 million images, which have all been labeled by a lot of online users, basically, in Amazon Turk. So yeah, people online were classifying these images with labels, and we start with that as a dataset. And this dataset has 1,000 types of objects in it. So what it means is that, for example, this image will be labeled by container ship. Okay, so instead of having a dataset with 10 handwritten numbers, 0 to 10 or to 9, we are going from categories from 0 to 1,000. Okay, well, before the nominal work of 2012, which introduced AlexNet, all of these models were sort of shallow and maybe even not non-neural network approaches. And yeah, just to explain one thing is that the top 5 error, what we see here plotted, top 5 error is that if we have a model which will we will allow it to give us 5 most likely predictions for any image, we will count it as correct if at least one of those 5 classification it gets is actually the correct class. So it sort of has like 5 guesses, and if at least one of them is correct, we will take it as okay, that's correct. That's a correct classification. And so you could see that in 2010 and 11, the previous models were working with 28%. What is it? 28 or 25 error of top 5 means that it was wrong in 25% of cases, while 75% of images it got correctly. So for 75% of images, amongst the 5 classifications that it gave, at least one of them was correct. But in the roughly 1/4 of the data set, it was actually wrong in all of those 5 guesses. Okay? Just by the way, human performance is somewhere around 5%. Okay? And what you can see here, that kind of that there is a very substantial change in these 2 results. So with the usage of AlexNet as a model, the error was reduced by roughly 10%, which is quite fast when you look at the human performance. You're getting closer and closer to the human performance by just using different models. Okay, and so AlexNet model was the first one which used convolutional neural networks, and ever since then, on the data set this large actually, ever since then, all of the later models used in these were actually also deep convolutional neural networks. So this work is a sort of wake-up call for the whole machine learning field, I guess, that these deep convolutional neural networks work very well on various types of data, and that they can sort of reduce the errors that people were getting with some other methods before. And so you can see that over time, this error was getting much better and better, all the way until actually surpassing the human performance. Right. Well, and today the result is somewhere around 2.3%, and there are different types of results as well, because some are including some new data that they trained the model on. So I don't know if to include them into the statistics either, but still we are sort of getting better and better at this data set. Okay. So one more thing that you can sort of see on this graph is that we have used 8 layers in this case. The later models were using something similar, but the later models were using deeper and deeper networks. So the idea was that if you include more layers, you can sort of learn the representation in a better way. Well, there are some caveats to this, because there, of course, people here were also trying to include more layers, but they were failing at some at the test results, because there you have to sort of include some more tricks. So year by year, you can see there are many additional sort of tricks how to handle larger models, how to still maintain the capability of the model to learn, while still sort of not overfitting it. And so there is a lot of details with all of this, which I will basically not go into right now, because that's besides this point of this class. The takeaway message from this is that ever since the AlexNet, all of the other following models were using deep convolutional neural networks. Okay. Right. So we touched briefly on this, and that was the concept of having an image, then data-driven feature extractor, which is sort of converting this image into a vector representation, and then having a classification, which is sort of just doing the simple task of combining these numbers into the class. So classifying it with a label. So there is some additional effect that we can sort of get from this outline, and that is actually but by dropping some parts of it, we can still explore, use some parts of this pipeline to our advantage. So if we were to drop the classification part of an already trained network, we will have a image into a feature sort of translator or a network which will sort of represent our image with some vector. So this part of the model becomes useful as a general feature extractor, because the sort of its representation ability depends on the data it was trained on. So if we train this network on a dataset as large as the ImageNet, which included million of images, we can expect it that the representation ability of this network, sort of the ability to compress images into some intermediate representation, will be quite large. And because there were so many images in the original dataset, that this representation ability will be quite capable to describe any other images as well. So this is something that we can use in all sorts of ways, basically. One particular type that we can sort of use this as is that we will have the image to feature part of the model. So here, image to vector v. And we can use that as just a simple feature representation. So let's see that we sort of represent these two cats and this car into 3 vectors. We will see that these, and that, let's imagine that the dimension of this feature is 2, that we have just two neurons here. And that if we were to plot these as a points inside this 2D space, the images of the cats will be encoded into a vector which is very close to each other. So they will sort of fall nearby each other in the representation space. Whereas the image of the car, if it were to be sort of again fed through this this pipeline and sort of extracted at this moment, we would get a vector which would be a number which is somewhere on the plot, but it would be sort of far away from the original images. And so what you can use this for is to search for some similarity in between images. And probably you know this from the Google image search, where you can sort of upload an image and tell it, hey, this is my image, I want to search for anything that's similar to it. Well, the underlying technology there is that they will encode these images into sort of by this pipeline. So they will encode the image into a feature, and then inside this feature space, in this simplification just 2D, they will look at these distances and tell you, okay, in this query image here, this first cat that I got, I am seeing that this encoded other image from our dataset, this other cat, is actually quite close. Whereas this other image that we encoded, which contained car, is actually quite far. Well, so if I'm searching for similar images, I will probably give you these rather than showing you some far away images. Okay. So this conceptual thinking about sort of feature similarity goes even beyond. So if we had encoding of these images here and then here, so all of these points are sort of these vectors, right? You can almost even look at the path between these two images inside that representation space and sort of find what images line or lay on the same line or very nearby to the line. So you can sort of see inside this representation space that we got in, using this model, and when we represent all images that we have, you can see, like, basically you would have to represent whole data set of images inside using this model into these feature representations. Then you can see that somewhere in between this image, let's say, and then this image, there are these images somewhere on the path. Well, if I were to, if you remember a little bit from our previous class, from the first one actually, we had a demo of the Mario Klingerman's work, X Degrees of Separation, where the task was basically the same. You had one image here, which was somehow represented into a vector, and then you had some image here, which was again represented into a vector. And then the task was to find everything which lies on the path between these two images. So this is very similar to what we were showing here, where this is the first image encoded, and that this is the last image encoded. And then if we have a data set of images from galleries, then we can sort of explore what lies on this path between these two encoded images. So to sort of explain it here again with the formula, well, if we have this first image here and then encode it into a vector, and then if we have another image here, image 2, and then encode it into another vector, in a vector space, we can sort of go on this path, sort of interpolate between, and then check with all the other images in the dataset. And you can imagine that this is quite like all the other images, this will take a lot of time, right? Depending on your dataset, of course, but if you have a lot of images, this will take a lot of time. You can check with every one of those images and kind of see the distances between these two images and the one that you are currently checking, and you can maybe pick the ones which are somewhere on the path. And this is something that we will sort of explore today in the more practical session. So today's practical session will be again starting with the notebook that is on our Git repo, and it will talk exactly on this about this. So it will explore the image similarities using convolutional neural networks which have been already trained. So something either like the AlexNet or other networks as well. Okay, so if I just briefly show you the web page, is on our Git repo in the third week, and what we will be doing is that we will be reverse searching for images using some other sort of pre-trained network. Just a short note, this notebook that we will be using today is something that I will be reusing from other classes. So I first saw this network being used at the machine learning and art class that I took at CMU, and then I discovered that it's actually being sourced by some of the networks from ML4A, which is actually a really good resource. And they have tons of these notebooks with even more advanced tasks. So a lot of this text is described by the authors of ML4A, which is Gene Kogan probably, and he's really good at explaining everything. So it's a really good notebook, which is why we will be reusing it as well. Okay, so more about that in the practical session. Okay, I will just show the ML4A guides. So this is a website which has all sorts of tasks that you can do with all sorts of types of neural networks, actually. Reverse object search would be something similar to what we would be doing today. And I think maybe there is a reverse image search, that's the one, and then searching for two paths, shortest path between two images. So these two are somehow combined into the exercise that we will be exploring today. And it's quite likely that we will see some of these in later classes as well. However, if you are interested, you can look at these yourself and explore them, sort of just run them and then see what happens there. Okay. On the next week, so 8th of May, there is actually the bank holiday, so there is no class. Which is good, but it also means that there will be some more homeworks, but I will get into that later, which is less good, right? On the 15th of May, we will have, so that's the following week, we will have an invited guest lecture by Rebecca Fiebring. Well, she is a creator of the Vecinator, and so she will be showing you how to use this tool called Vecinator, and then also talking about some sort of interaction design and how this relates to machine learning models and the using of those. Okay, well, so I mentioned already that there will be homeworks. One of these homeworks is another reading, and the reading for the next class, so the 8th of May, will be this one. This is the paper which introduced the network that we now call AlexNet. So this is the paper from 2012, which basically caused the whole machine learning revolution, you could say, which has shown how powerful these models can be. So I think it's quite important paper to read, because it sort of describes quite well what happens and which approaches they used, and yeah, it is quite technical. However, with the topics that we covered today in the class, a lot of those things that they're explaining there should be something that you will already understand, and maybe some terminology there will be some sort of more details that you can sort of add to the understanding that you have from this class. Okay. So while our first reading was mostly more or less optional, this one will be something that I will be checking, and so there will be a some sort of submission of some sort of summarization that you will have to do. So I think there will be a sort of like one paragraph or a few paragraphs of text that you will have to write to summarize the paper after you read it. And I will also prepare some questions, probably multiple answer questions for you to answer, or maybe some open-ended questions as well. And so this will be something that will appear in your Moodle, and the deadline will be on the 8th of May. Okay. So inside this paper, it's much shorter one actually. I will open it. It has 8 or 9 pages. Yeah, 9 pages. There are some technical details in there, and some of them you will be able to skip or skim through, but it is still quite readable, I think, when compared with other papers. So the parts that you can skip is these chapters, or not skip, but just like skim through them. The 3.2 training on multiple GPUs, 3.3 local response normalization, 3.4 overlapping pooling. So this is something. These are some sort of details, hacks they had to do to fit the model on multiple GPUs when training, and then some tricks they used for to sort of minimize their errors. However, these techniques are sort of outdated now, so it doesn't really matter if you understand them too well. But yeah, if you want, you can still go through them, but it's not necessary. I still would like you to read the rest of the article. So like all the way from the introduction with all the explanation of the dataset used, with the architecture, so the description that we were talking about today, all the way to fighting with overfitting, and some details, results, and discussions. Yeah. Okay. So this is the first homework, and that one you have basically 1 week to do this until the next week. There will be a second homework, but the deadline for that one is on the 15th of May, and the task there will be to sort of prepare yourself for the class that you will have with Rebecca, and this means to get to know the basics of using Vecinator. So there are some walkthroughs on the Vecinator webpage. There is also like a download webpage that you will have to go start with, install it on your machines, and then look at these walkthroughs here, and then follow them in order to be able to sort of to have some basic understanding of what Vecinator is. So when the class, when you will have the class, you will have some sort of basic understanding already there from this walkthrough, and you are able to do some more complicated and cool examples in the class. Okay. Yeah. So there are some bonus links at the. This is the end of the lecture, so these are some bonus links if you are if you want to read some more on it. We were talking about convolutional networks, so they are being shortened as convnets quite often. There is a good resource on the ML4A which explains also the history a little bit that we went through at the start of the class, and also some of the concepts. So if you missed some detail here, you can either rewatch it or sort of try to find it on your own, or you can use this resource to sort of give you some more details about the networks. And then there is the resource of quite a lot of handy notebooks, which we will be using one of them today or two of them today. Okay, so thanks for your attention. Hope you liked this class, and see you on the practical session.